Embedded system security refers to the measures taken to protect embedded devices and systems from cyber threats and unauthorized access. This includes various hardware and software measures, such as encryption, secure boot, firewalls, and access control mechanisms. It is important for embedded systems to be secure because they are often found in critical infrastructure such as medical devices, industrial control systems, and transportation systems, and a security breach can result in significant harm. However, embedded systems can be vulnerable to security threats due to their limited processing power and memory, and their lack of constant software updates. It is crucial to address security issues during the development stage to ensure that security is built into the system from the ground up. There are also various industry standards and guidelines for embedded system security, such as the ISO IEC 15408 Common Criteria, and the IEC 62443 series for industrial control systems. Embedded system security involves several different aspects that must be considered to ensure the security of the device or system. Here are some of the key areas to focus on. Physical security. This involves measures to prevent physical access to the device or system, such as casing, tamper-proofing, and secure boot. Network security. This involves protecting the device or system from network-based threats, such as malware, denial of service attacks, and unauthorized access. This may include firewalls, VPNs, and encryption. Access control. This involves controlling who has access to the device or system and what they can do with it. This may include authentication mechanisms such as passwords, tokens, or biometrics, as well as authorization mechanisms such as role-based access control. Data security. This involves protecting the data stored on or processed by the device or system, such as encryption, secure storage, and data backup. Software security. This involves ensuring the security of the software running on the device or system, such as secure coding practices, software updates, and anti-malware software. Cryptographic security. This involves using cryptography to secure communication, data storage, and access control. This may include symmetric and asymmetric encryption, digital signatures, and hash functions. Supply chain security. This involves ensuring the security of the components and suppliers involved in the creation of the device or system, as well as the security of the supply chain itself. These aspects of embedded system security must be considered throughout the entire life cycle of the device or system, from design and development to deployment and maintenance. It is important to stay informed about the latest threats and technologies in the field and to regularly assess and update the security of the system. Here are some common techniques used to ensure embedded system security. Encryption. This involves the use of mathematical algorithms to encode data and protect it from unauthorized access. Encryption can be used to protect data in storage, as well as to secure communication between devices. Secure boot. This involves verifying the authenticity of the software running on a device before allowing it to start up. This can help prevent malware and unauthorized software from running on the device. Firewalls. This involves using network security devices to block unauthorized access to a network or device. Firewalls can be used to enforce access control policies and protect against network-based attacks. Access control. This involves controlling who has access to a device or system and what they can do with it. Access control can be implemented using passwords, biometric authentication, or smart cards. Virtualization. This involves running multiple isolated operating systems on a single physical device, each with its own security boundary. This can help prevent security breaches by containing malware or other threats to a single virtual machine. Trusted Platform Modules, TPMs. This is a hardware security module that provides secure storage for cryptographic keys and other sensitive data. TPMs can be used to secure boot sequences and enforce access control policies. Sandboxing. This involves running untrusted code in a secure environment, isolated from the rest of the system. Sandboxing can help prevent security breaches by containing malware or other threats to a single environment. Secure coding practices. This involves following best practices and guidelines for writing secure code, such as avoiding security vulnerabilities and implementing secure data handling and storage. These techniques can be used in combination to provide a layered approach to security, with each layer adding additional protection against potential threats. It is important to regularly assess and update security measures to stay ahead of evolving threats.